Hi guys, and welcome to this video cast, which is about database indexes, why they're important, how we create them, how they work. And this is specifically designed for Microsoft SQL Server, but actually the same principles generally apply to all relational database management systems. So you can apply most of this information that you can learn from this video elsewhere. Now, the reason I'm producing this is not because I'm an expert, because I'm not a database expert by any stretch, but actually there are lots of articles on the web, blog posts, which, to be honest, I don't find particularly useful, because trying to read a load of text and understand what the person's saying can be quite tricky, whereas listening to somebody describe it and to show examples is much kind of more effective, and hopefully will take less time than trying to read some kind of online guide. So the first thing is that indexes really are concerning the performance of your database system. So if we have a table and we want to do something like select a load of data, this runs, it's going to come back with a number of rows. That actually takes an amount of time. In any production system, the amount of time that takes at some point as the server gets more and more loaded is going to become a problem, because if disk I/O starts getting past any reasonable limits, the system's going to start slowing down, the CPU is going to start slowing down, you're going to get memory starvation and all of the problems that could occur because of that. So to keep our performance optimum for as long as possible means that we keep our databases running for longer before we have to consider much more significant changes like architecture changes, engine changes, and cloud changes, or whatever else it is that you're considering. So SQL Server actually performs a number of optimizations for you automatically. So when you run a query, it caches certain things that it can reuse. It caches the execution context. So if somebody runs the same query with the same parameters in a short amount of time from the previous time, then it remembers how to go and do that query without having to build it all up again. But by and large, we obviously can't rely on those doing exactly what we need to do. And although they're optimizations, they only kind of make the most of what is there already. They can't really understand your data as well as you can. And if you've got any kind of system where you're going to be scaling up to potentially thousands of users, millions of rows of data, those kinds of things, then without indexes, there's no way that your system's going to be able to cope with the burden that's placed on it. And there is a kind of a question about premature optimization. Do I want to optimize my tables and my queries now, or do I want to do it later? But in most cases, premature optimization is a bad thing, because you might be inventing a problem when there isn't a problem. But likewise, sense and wisdom would say, if you have a table that is going to end up being millions and millions of rows, then there's a good chance that performance will be a problem, and it's worth looking into kind of identifying indexes that could be created and then creating appropriate ones. So we just need to define really a couple of terms. The first is a clustered index. So if we open up one of these where I've actually created an index on it, this table here, you can see that there's a clustered index. So a clustered index, which we'd usually call the primary key, is effectively the ordering of the data in our table, how it's actually stored on disk, in terms of there's a big linked list, and the linked list points to data locations, points to pages, and they're put in order of the primary key. So that kind of means if your primary key was, say, a number, just a simple integer, that if I want to find item 1, 2, 3, 4, because the clustered index is in order, I can very quickly find item 1, 2, 3, 4, and I know exactly where to look for it, because just like a telephone directory, if things are in order, they're much easier to find. A non-clustered index is a slightly different beast. It's to do the same job, but it does it in a different way. Really, what a non-clustered index does is it almost creates a virtual level above the clustered index if there is one, or above the heap if there isn't a clustered index. And so what happens here is the data in the pages isn't ordered by the non-clustered index keys, and that's just because it's already ordered by the clustered index keys, so it can't be ordered in two different ways. But what actually happens is the index itself is ordered, and when you kind of go down the index in the same way that you can very quickly find an item in an ordered list, you can find an item in here, and then that will have a pointer to the primary key index, which then allows the query to go directly into the data page and to find out where the data is. So a non-clustered index can perform almost as quickly as a clustered index. We'll see that later. But the thing is, you can only have one clustered index because it's an ordering of pages on a disk, and you can have as many non-clustered indexes as you want. Now, it's worth kind of just discussing the trade-off here. If indexes are so good, and if they give you all of this kind of performance of querying, you know, what cost am I paying? Why wouldn't I just create 50 indexes on every table? Well, there are two things really. The first is in terms of just the index size. So depending on what columns you have specified as your key columns in your index, the index itself can end up getting quite large. So I've seen a table where the general data size was about 300 gigabytes, but actually the main clustered index was 100 gigabytes. So significant size overhead for large tables, or potentially, obviously depending on how many columns you're including in it. So there is a size overhead. The second reason is in return for your improvements to the read performance, because indexes really are only about queries and selecting data. In return for that, you're taking an amount of hit on your inserts, your deletes, your updates. Because if you have an index which is like a telephone directory and you want to remove an item from that index, then effectively you might have to move all of the other items around a bit, you know, change the index, remove an item from a list, all those kinds of things. So as well as the underlying table data, which obviously would be updated, you would then need to update every index that you have if the column you're changing is included in the index. So you're paying a bit in the kind of write performance in return for massive improvements in read performance. Generally, the write performance doesn't take too much of a hit. Obviously that gets worse with the size of the table. Generally you want kind of as many indexes as possible, to cover as many kind of query scenarios as possible. But we'll look at that, what that actually means in a minute. So what am I doing here? I have a SQL Server Management Studio, which is pointing to my local desktop machine where I have SQL Server running. I have this database called Wide World Importers, and this is just a Microsoft test database with tons of tables, tons of different sorts of technology and tables and views and all kinds of stuff. And it's really just a kind of a demonstration database, but I've got that just because it's an easy way of getting, you know, temporary data just to play around with queries and learn a little bit about indexes. So I've taken that and then I've created 7 tables here. So I've got a customers table. This is basically copied directly from the customers table in here. And then I have a number of invoice tables. The first 4 of those are basically copies of the invoice table. The last 2, if we look in here, are literally just a single column of invoice IDs, which again are taken from the other table. And they're just to demonstrate some of the different scenarios of what happens when you're actually running your queries against these tables. Just as kind of information, this is a proc I created with some script I found online to show me all of my tables, how many rows are in each. Obviously the invoices all come from the same table, so they all have 70,000 rows. Not massive, but large enough so that we can get some useful numbers from the queries. And then the customers table, which we use for joining later on, is a much smaller table. You can see here that this is about 0.5 meg in size, and these are about 60 meg each. So not tons of space. They're not going to be taking up lots of CPU or memory when they're running. But that's just to give you an idea of what we're actually playing with. So the first thing is, if we just pop in and just look at, say, one of these. So this here is the simplest table. This is a single table of invoice IDs. It has no indexes on it, no primary key, which I'll call it a primary key, but it's a clustered index as well. No primary key, no index, no nothing. So this is really just 70,000 rows of numbers, because the invoice ID is just an auto-incrementing number. And notice here that in your studio, you've got a couple of buttons. So this button here, Control and M, include the actual execution plan. So what happens is, once it's run the query, this is what we're going to be spending a lot of time looking at. SQL Server helpfully tells us what was happening and how much relative to all of the commands that were happening, how much of it was down to this query. Now, we're only running one item here, so even if that was really, really slow or really, really fast, it's still going to be 100% of all the time. So at the minute, this is not very useful, but you'll see why it's useful later on. Just a little note here. If you click that button instead, you can include live query statistics. And the reason that's useful is if you have a query that's taking ages and ages and ages to run, and you don't really want to leave it running because you're not really sure what's going on or why it's taking so long, you can click that button, and as you run it, a tab here will continually update with what's happening. And that can help you see if you've got a problem, and you can see a certain table growing, a certain query growing or something, certain memory usage going up. You might be able to see what you need to fix in order to get that working. We don't need to use that because our queries here will run quickly enough. The other thing that can be quite useful is that button there, include client statistics. And what happens here is, if I run this again, F5, you notice I've got a new tab here. And this will show me every time I run a new query, this will show me the difference in what's happened. So I've obviously been running things earlier in the day. So this is now saying, right, and in this most recent one, it's telling me how many rows were returned, how many bytes were received, and kind of processing time and things like that. So if I change this, for instance, and let's say I try to star instead of that particular column, I can run it again and see whether that actually looks any different. And interestingly, it is a little bit different, which is, again, worth looking at. But part of that is probably because it's cached the execution plan. So you notice that some of these numbers are changing a bit. So trial 10 is the same as trial 8, but you can see here that the processing time has dropped. And that's almost certainly because the query plan from this took some time to build and has been reused. But that's kind of quite useful sometimes. We'll just turn it off for now, and we'll go back to this. So what we can do here, and this is really kind of one of the important kind of techniques, is we can compare what happens when we do two different things. So as well as invoice ID only, I now have invoice ID only with a primary key. And literally the only difference between these two tables is I've told this table that this is a primary key. So this is now running as a clustered table, which means all the data is going to live in order on the disk. And this one here doesn't have that. So this is just going to be basically a massive heap of stuff. And we're going to start by just basically selecting the same column from both and run it. And the cool thing here now is, because I've run these as a single batch in the same window, I can now look on here and I can notice that the two kind of key things that we're looking at is how much time or how much of the time total was taken by the first query, how much was taken by the second. Now in this case we can see that they were both about as fast as each other, and because this is a kind of a 70,000 row table, this is probably fairly accurate. If we only had one or two rows, possibly it would be so fast that it would be hard for the query optimizer to measure accurately. But this is kind of saying that they take about the same time, but straight away that we can see there's a difference between the two. And this is where we need to kind of start getting this idea of a table scan and an index scan. and then we will see an index seek later on. I mean, this actually tells us that it was using the clustered index, which is usually the best index to use because it's in order. So what happens here is when you run these things, SQL Server itself is going to say, right, what columns do you want from what table, what indexes exist, what can I use, what can't I use. Now, in the first case here, it's very obvious that without any indexes, SQL Server has no other choice except to scan the entire table. And that table scan is about the slowest way that you can run a query. So even if this, I mean, this has only taken like less than a second, but the fact that that's using a table scan is already an alarm bell, because what that means is as that table grows, that's just going to get worse and worse and worse. And that is, you know, because it's a small table, that's probably been read into my machine RAM. But if I'm running a big database on a production system, well, this query has to share the resources with every other query that's running at the same time. So even if my 16 gig of RAM can handle a 60 meg table loaded into memory, if you've got a server that's running thousands of queries at the same time, and you start paging stuff to disk or having to scan it on the disk, then these things are going to become slow very quickly. A clustered index scan is basically saying you've got an index, it's clustered, it's in order, but because you want all of the invoice ID from every row, so you've got no where clause, effectively I still have to scan through the entire thing. So it's not really going to save me any time scanning through data that's not in order compared to scanning through data that is in order. It's not going to really make any difference in this case because I'm not using that ordering to my advantage. If we look here, you can see that actually the return result set is the same, and that's almost certainly because the ordering of this data in the table I copied from is in order. So it's probably been written to disk in the same order, just basically because that would have been the easiest way to do it. If I would have jumbled these numbers up first, then this one would have come out in order, and this one would just come out in the order that it happens to be in the heap. So we can see straight away that what we're doing with our query optimization with understanding indexes is working out here whether we're going to get a cost saving. We can compare two things, and this is dead easy to do. Like I say, SQL Server's doing all the hard work. And in this case, as I say, we're returning everything from a non-index table and everything from an index table. Obviously, or hopefully you can see that there's not really going to be any time saving by doing it one way or the other. Just a quick note in terms of actually creating a primary key. The normal way to do it in SQL Server is you go into the design view, and then you can right click this and set it as primary key. Obviously this one's already set there. I think you can put it here. Identity is it's not an identity. Okay, no, it doesn't have it in the properties. I thought it had it in the properties. So you can do that. And obviously you can also have a primary key made up of more than one column. So sometimes, especially in, say, a link table where you might be linking, say, a customer to orders, you could just have a customer ID in the order. But if you've got a many-to-many relationship, the link table might just have two columns and they both form the primary key. And again, it's just a way of ordering the data so that your queries can find what it needs to find really quickly. So just out of interest, if we use select star rather than select invoice, is there going to be any difference? So these are the kind of questions we can ask. Now remember, this table only has one column, but one thing that you need to kind of understand about SQL Server, about query optimization, is you can't always assume what you think is going to happen. So in this case, we run it, we look at the execution plan, and again, maybe not particularly surprisingly, we've got kind of a 50-50. And this is the non-index table, so it's using a table scan, but actually the same thing would happen here. So your assumption was probably that it would take the same time. Your assumption was correct, but your assumption is not always correct. So that's why we test things. That's why we have the query analyzer. So whether it's using the clustered index or the table directly, in this case, it's clever enough to know that star is the same as one column. There isn't any overhead with doing that. The interesting question will be what happens if we've got 10 columns in the table, and you know the difference between, say, selecting star versus selecting, you know, only the columns that we need. So the first place where we're really going to see a benefit of running an index, and in this case again we've only got one index, it's clustered, it's the primary key. This is still the table that only has one column, but this time I'm just picking a random number. I mean, it doesn't actually matter what the number is. Let's run this against both tables. So there's only one column, it's returning back exactly what we specified. But now let's look at the execution plan, and immediately you can see that this clustered index seek is only 2% of the overall time. The table scan using the non-index table is 98% of the time. In other words, this is almost 50 times faster than that. And remember, this table is only this table was quite small, wasn't it? It was only about a meg, I think, 1 meg. So it's not a big table, and already we're seeing the difference between having an index. And what's happening here is this word seek. Sorry, every time I try and put my mouse there, it covers it up. That word seek, which you can see here, is significant, because that seek is saying, because you specified a value for a column that is in the clustered index, because remember, invoice ID is our primary key, because that's the value you've specified, I can go very, very quickly into the right place, a bit like opening the telephone directory in, you know, under Z or whatever, you know, knowing that you're trying to find something that begins with Z in order to find your item as quickly as possible. And you can see here, this is a tiny column from a tiny table. In fact, if I could just go back and find under here, I can't remember what that proc's called, proc size stats. If I run that again, proc size stats, we can see here that these small tables, what are they? Yeah, one meg each. So 70,000 rows, 1 meg, tiny table, massive difference already. And this really is the ultimate intention of index design, is getting numbers like this and saying, right, this one simple improvement of a primary key has made this much difference. And if you look here, obviously there's an overhead to maintaining that clustered index, but look, it's hardly anything. So that's just under a meg, that's just over a meg. So that the cost of that index is pretty small really, and the benefit in speed is massive. So really our ultimate intention, and there will always be a cost, like I said earlier, is to try and get things using indexes wherever possible, and we need to find out how that's going to work. So let's have a look at the larger table. So this table now has all of the columns in, and if we run it, you can see what's in there. Tons of stuff. 75,000 rows in each one, or 70,000 in each one. And again, if we look at the execution plan, it looks pretty much like what we saw in the first place. So by returning all of the columns from both, we're not really benefiting from any kind of index. We're either scanning the entire table, which is basically a heap, or we're scanning the clustered index, which is basically an ordered set of pages. So again, not really much benefit there. We probably wouldn't expect any benefit when we're doing that. And what happens then if we select a particular column? Now, if you remember, invoice ID is part of the index of this table, whereas this table doesn't have any indexes. So I would expect this one to be much faster. If we run that, we can see here that actually there isn't a lot of difference here. Now, why isn't there so much difference between these? So if we look at this again, we can see that because we're returning every row, we still have to basically scan the entire table. So we're still not really getting any benefit from the index when we're, even though we only want the column that's actually in the index. So indexes are not about kind of speeding up the select statement. They're about speeding up the where clause, which we'll find out now. So again, we've already seen this on the smaller table, but let's see what happens on the larger table. So again, doesn't really matter what number. So we run that, And we can see here that again, this is the difference is even starker here. So that's basically saying as good as 100% of the time this took was due to the non-index table, whereas basically 0 happened on this. Why? Well, again, all we have to do here when we run the query is we load a relatively small clustered index, and the data we want is actually in the index, so we don't even have to go into the page data of the data table to pull anything out. We're just kind of saying we've got an index, we don't really care about the other columns, they don't even come into it, and as soon as I've kind of whizzed through that index, I know exactly which part of that index to hit because I've specified that number. Whereas here, again, I'm having to read through everything. Now, interestingly, this has actually sped up the table scan by parallelizing it. And what that means is, well, my desktop here has got whatever, it's got 4 cores in the processor. So SQL Server can use all 4 cores to effectively run 4 separate table scans on a quarter of the table each. And again, that's going to speed it up, but that's obviously at a cost of CPU cores. And even though it's done that and made that 4 times faster, you can still see that that's almost all of the time. And because that one's so slow, you can see here that the query analyzer is actually telling you that really you're missing an index. Look, 99.5% of all of this execution time was because this index was missing. So they kind of suggest what you could do. Create non-clustered index. You could give it a name on the table that you've just been running it against, and it even suggests which column to include. Now, you could run that, it would work. You'd need to give it a real name, and this particular query would then speed up. We'll see that in a minute because I have one with an index on it. However, what you need to consider is, well, if I'm going to have to do this for a number of different types of queries on my system, would it be better just to create a single index with maybe 4 columns on it, rather than 4 separate indexes with maybe 1 or 2 columns in each one? And there's not necessarily an easy answer to that. You might need to do some testing to work out how much kind of performance overhead you create by having to update 4 indexes every time you write to the table, and then the speed of which the separate indexes are going to make your queries better. And that's kind of another really important point here, is this is all very much relative to your system, the way it gets used. Do you have a heavily read-only system? Is it 50-50 read-write? Is it a kind of system where 99% of all the work happens in one page that calls one specific query that needs to be kind of the fastest part of the whole system? So there isn't always a specific answer. Should I have 1 bigger index or 10 smaller indexes? There's no specific answer to it. The specific answer is you would need to test it for your scenarios. And actually, there might not be a noticeable difference between them, in which case, choose whichever one you want. So we've run this, we've seen that returning a single column where we have a clustered index, or any index in fact covering that, then is very, very fast, which is kind of the whole point of the index here. We're kind of saying, let's have a telephone directory. Rather than searching through a whole list of everyone's name and address, I'm going to go straight to the person, pull them out really, really quick. But let's find out now what happens if we return a non-indexed column. Now, in this case, notice that we're going to be pulling back all of the rows again. So we run that, and again, table scan, clustered index scan. We're not saving any time because we're pulling back all the rows. So even though that one's got invoice IDs in the index, I still need to read everything back, so I'm still going to have to go through the whole lot. No real benefit. So let's go back to doing the same thing, but using a specific invoice ID. So order ID in this case is not indexed on here. So this is the primary key table. It only has 1 index. That index only includes the invoice ID. Invoice all is not indexed at all. So if we run these now, we'll obviously get back our results. And if we look here again, it's quite interesting that you kind of think, oh, hang on a second. If that column isn't indexed, then why isn't this one really, really slow? Well, the simple answer is that a clustered index, it really sits directly on top of the data that it relates to. So even though that column itself isn't in the index, it is effectively right next to the clustered index. So in this case, invoice ID and order ID, I find the invoice ID in the clustered index really quickly, and then that points directly to the row of data where I can go and get the order ID very quickly. So even though that's not an index column, it's still really, really fast. And remember, the index is about the where clause more than it's about what you're returning. But what you're returning is relevant, which we'll see later on. As expected, the non-index table is back to the table scan. I've got to just dig through every single row until I find one where the invoice ID matches that number, and then I'll fetch the order ID from it. So the slow bit is actually finding that row, and then the fast bit is then getting the columns. So if we then change this around a bit and say, well, what happens if instead of using the invoice ID and the where clause, what happens if we use the non-indexed column in the where clause? So we're still returning the same two columns, so we'd hopefully get those same results as that. But this time the where clause is different. We're going order ID, which is not indexed, and that's what we're doing in the where clause. And look, lo and behold, we're back to 50%, 50%. So this is, again, kind of saying, well, if we don't have an index to help us find the record, or the row that has that order ID, then I don't have a choice. All I can do is scan through the entire index until I find the one that has the order ID of 449. But once I found that item, obviously it's not going to take me long then to return these columns. So there's not really a lot of difference there. And again, Query Analyzer is trying to be helpful and saying, well, you could add an index onto the table. So table scan, cluster index scan, not a great deal of difference here again. So let's then say, well, imagine this was your system. Imagine you're looking at one of your queries and you're saying, well, actually, I often need to do a lookup by order ID from the invoice table. So, and this is a very common scenario in any kind of, sales management system, project management system, is you might look up an order by the customer, by its ID number, by the business department, by the value. There's so many things you could be using essentially in your where clause, that is the kind of tables that you end up potentially having to create multiple indexes for. So I've created one here, invoice all PK and an index. So this index here, and just in case you want to know how to do it, to create a new one, you just do new index. If it has a clustered one, you won't be able to create another one because it can only be ordered by one thing. And there's all these other crazy stuff, but let's not go there for now. And then it basically says what do you want in your key columns. And this is relevant for the where clause. We'll see that in a minute. And then you could include columns, which will show you why that's important later on. So the index that we already have here, non-clustered index, non-unique, if we go into there and get properties, it will tell us that effectively I've added a second index. So I've got the clustered one, which is invoice ID. I've added a second index, non-clustered, with a single column in it. So nothing included, a single key column. And I'm going to add that to our list of tables. In fact, we ditch that one. That is index. Now what happens when we run these? We can see here again that by adding that index, we've immediately taken what we had, which was this. So remember, this does have an index. It just doesn't include order ID in that index. So that's still having to scan the entire effectively the entire table. Whereas in this case, we can say, well, at index seek, I've got an order ID. It's in that index, so I can very quickly go into that index, find the clustered row ID effectively of the data I need, and pull back anything that I want from that. So, that's really super fast. But then here's a question. What happens if I want to pull back a column as well? So let's look at our index one for now. What happens if I want to do this? In fact, I will actually compare it to the primary key. If I want to pull back customer ID is not in either of those two indexes. So would you expect this to now be as slow as this one? Or would it, or will it still be fast and that one would be slower? So until we added that column, we were saying that this second one was really fast because order ID was in the index, or actually that order ID is in the index. What happens if we want another column returned, but we still have the same where clause? And the answer is actually that this one is still faster. And why is that? Well, remember I said that indexes are primarily about the where clause. So what they're saying is the index is used to find an item, so then I can go straight to that item. It's a bit like getting an IKEA row, and you go to the warehouse, don't you? You go down one of the aisles and one of the positions. Is if you get that number, you can go straight to the item you want. Now, once you're at that item, of course, you can pull back whatever columns you want because you're already there. Whatever columns I need are irrelevant because I've already found that row. So I've got the customer ID, that's come back as well, but that's still super fast. What's interesting here, however, is this extra slightly different piece of graphic that we haven't seen before, is this key lookup, and it says it's clustered. So what does that mean? Well, what that means is, well, although I found the order ID in the index, in that non-clustered index, invoice ID is the primary key. So one thing that I didn't mention is the primary key is already implicitly included in every index you create. So when you create an index, you don't need to add the primary key column as well. It will be there. So when I was just getting these two, effectively both of those exist in that index. So I don't actually have to go into the clustered index data itself to return those two pieces of information. Effectively, that's a bit like having a little two-column table, which I can just say, well, here you go. But as soon as I want that third column, which isn't in the index, although I know where to look, so this is still very, very quick, I still need to then say, right, you found it in the index, I've got the effectively the primary key number, I now need to use that to look up in the clustered index the actual data to go and get that additional column. So although I'm doing a piece of extra work, it's still blindingly fast because it's right there. Like I say, yes, I have to go down the aisle and find the place where my furniture is in IKEA, but because I know where that is, that doesn't take a lot of extra time over, again, scanning through the entire index looking for order IDs. So that's pretty cool. So then what happens here using index with included columns? So if I have, I've got another table here, and you could say, well, okay, that's kind of okay. Maybe on a bigger table, is that going to start being a problem? Well, maybe, maybe not. Again, you measure these things. So the next thing I'm going to show you is not necessarily something you would have to do straight away, but I want to kind of show you what it looks like when you include a column in an index. So if we look at this table here, we'll notice it has an unclustered index. If I get a property, unlike the other index, as well as the key column of order ID, I also include customer ID. So I've got both of those in there. But what does that mean? So let's actually have a look here. Let's compare this one. So what's that? Index underscore inc. So the first thing to note is if I run those two, you notice that the one that we looked at previously does its key lookup. So it's got the index itself doesn't contain the customer ID. So I have to do the extra key lookup. But look here, that because I've included column in the index, it's a bit like saying, well, it's not ordered by that, so it's not really good for looking up a customer ID. But in terms of actually getting the data back, look, index seek, the fastest of the fast. That's basically the holy grail of a fast query, isn't it? So Is that in real life going to be loads faster than that? Well, maybe if I'm finding one item, maybe not, but the order might actually be in a range. It might be order ID, less than 100 or greater than 100 and less than 600. So maybe those key lookups are going to start kind of adding up. In fact, we could try that, couldn't we? Should we try that? And order ID is less than, I don't know what let's just say 20,000. So if we try this and see whether there's any major difference, there, and run that again. So if you look here, there's still a bit of difference here. So what's actually happened here is it doesn't like using the order ID in the range clause, so it's actually removed the ability of that first query to actually find things by order ID, which is interesting. However, in the index one, you can see that the index seek is still able to use the range parameter there. So still a kind of a big cost difference. Is it a big enough difference to make it worthwhile? Well, that's always the question, isn't it? Again, test, measure, retest is always the way to go. Right, equals 449. So that's what happens when we have an included column. The next question is, what happens if instead of an order ID, what happens? Remember, this index here on this one has customer ID as an included column, not as a key column. So if I now look at but now I'm actually filtering by customer ID. That number's random, so don't worry that it's the same as that number. So if I just run this and look at what's happening, so if you look here, I'm not actually able to use my index seek anymore. This has had to scan the entire index. Why? Because including a column doesn't allow it to be used in the where clause. So including it is useful for columns in the select, because it means that you can get all the data you need from the index without having to go back into the table itself. But it doesn't work for the where clause. So in this case, if we did need to do this, then either we would need to create a different index which had order ID maybe included and had customer ID as a key column, or we could modify the index we already have and say, well, let's add customer ID into that as well. And in fact, we could do that now, couldn't we? Let's go into properties and go into here and say, well, rather than that, let's remove that one and add this one. Now notice that when we do this, this is going to happen very quickly because it's such a small table. Note that if you did that same thing in like on a real live table that was massive, rebuilding of that index could take a significant amount of time and disk and CPU. So don't do that quite as casually as I did. So we had an index scan. Index scan's better than the table scan because you're using less data because the index is smaller, usually, hopefully. But in this case, we've now modified that. The index has been rebuilt. So what happens now is, hopefully, as expected, index... Oh, that's interesting. Didn't seem to pick up on that index seek. I'm not sure if that's possibly because it's cache to query plan. So let's just add another condition on the end. So hopefully it'll use a different one. Index seek. Yeah. So now it's being able to use the index to find not only where customer ID is in the list in the index, but also then return all of those. So you can obviously do either of those depending on what you want to do. Right, I'm just going to put this back the other way just in case I need it for my next bits and bobs. Okay, it's going to apply those. So I also now want to look at joining tables because another issue with queries, I mean, these are quite simple queries. It's hopefully fairly easy to see what's going on. But then, of course, it can get quite kind of tricky when we start joining tables, because obviously you've then got indexes on more than one table to consider. So let's get rid of that. Let's look at this. So what we're doing here, don't worry about the red underlining, is we have the invoice non-indexed table. We have the index that has the primary key on it. the invoice table with the primary key, the index on it. We're returning invoice ID, which we would find in here in the index. Order ID and buying group ID, which we won't find in here, or they're not in the index. Order ID is in here. Customers has a buying group ID, and then we're joining these on the customer ID, which is, although these don't have foreign keys set up, the data taken from wide world importers would have this relationship established. And in this case, again, we're picking out a specific order ID. So if we run that, we can see some of the same stuff we got before, but again, something that we've seen for the key lookup, but now we see for a table join, is this idea of a nested loop. And as it says, a nested loop is an inner join. The cost is quite low because we're only returning one row. But when you look at these, when you're trying to analyze what's going on, it is possible sometimes, especially with more complex queries, is this table can get quite big, and you might find random little places where you go, oh, I've got a 99% of that whole query is just one table scan, and that might straight away, like this suggests, mean you need a non-clustered index on that invoice all table. But in this case, we can see kind of what we expect, that the clustered index is used on customers because we're using the primary key version of it. So what we're joining on is from the primary key, so we can use the index for that. It's going straight to the right item. Because we know it's effectively optimized this and saying, well, I know what order ID is. So once I know what order ID is, I can find the relevant row in here, and then I can do a really fast join onto that table. So it's not going to load both tables in, join them all, and then filter it. That would be crazy. What SQL Server is clever enough to do is say, well, what's the quickest way round to do this? And that's one of the reasons why you need to test stuff, because sometimes SQL Server will make a wrong assumption and something might be a lot slower than you think it should be. But if you look here, they're still taking about the same amount of time, and that's because here we're still having to do a table scan, we're still having to do a clustered index scan, because we're having to pull all of that back to then get the order ID, which remember is not indexed. But so we're still having to pull those back. If we change that to use something that was in the clustered index of that table, but not this one, then we would hope that that would turn into an index seek, and that would still be a table scan. So there's our table scan. That's now taking, unsurprisingly, all of the time. But because we're now searching on, remember, indexes are about where clauses, they're about filtering. That's now in the index. Clustered index seek, really fast. Go back to the loop, join that, clustered index seek, bang. Look how fast that is. It's amazing. So that's what happens when we join on that, which is an index column. And then the other question was, what happens if we join on a non-indexed column? So in this case, we use the customers table that doesn't have any indexes on it. So although that would normally be the primary key, in this case, there is no primary key. And so we're going to try the same thing. We'll try it first of all with the value that is in that primary key and not in that one. And and then we'll run that, see what happens. So again, not surprisingly, because this table doesn't have an index on it, that now incurs the table scan, because effectively the thing's got to look through everything in that table to find one that has the customer ID matching the one that we want from our invoice table. But in this case, because we're using invoice ID, then we get to use the clustered index seek on that one. So that's much faster, even though this still requires a table scan. And then if we change that again and say, what happens if we use the order ID? So order ID is not in the, not in the index of that one. But somehow, so that's using a clustered index scan. So although order ID isn't in the isn't in the primary key. The primary key is still clustered, so I can still scan the index, which again is not much faster than a table scan, if at all. But it does mean potentially on some tables where that index is much smaller than the whole table, it might be slightly faster paging through that than it would be paging through the table. But you can see here that again, if we use non-index columns, then 50-50, we're not really getting much benefit. So we've kind of looked at a few things here. We've hopefully seen, in summary, that an index is relevant for where clauses. So if we're trying to filter data in a query, which is most of the time, then indexes are really going to give us a lot of bang for our buck. So with minimal amounts of size and overhead, we've been able to speed up some of these queries by maybe 50 to 100 times just by adding something as simple as an index. Even though the tables are so small, relatively speaking, the index makes the query much, much faster. We've also seen that an index is not going to speed up your query, particularly if you're using a column in the where clause that doesn't exist in that index. Even if the items you're returning are in the index, the actual work required to find the row you want still going to require a scan, still going to be relatively slow. We've also seen that if the table and the index are not much different in size, then a table scan versus a clustered index scan isn't really very much different in speed, so you're not really going to get many gains. And probably the main kind of takeaway, as with most things in software, particularly when it comes to performance, is make sure that you measure stuff, check out what's going on, make an improvement, run the two things side by side, start learning how to understand these. So when we look at some of the larger, select statements and stuff, especially if you've got, you could have select statements in the where clause, all kinds of crazy stuff going on. Start getting good at what's happening here is, where is the meat of the work? Now, if I'm doing something that can happen in a seek, in an index seek, if I look at these and say, well, that's a clustered index seek, imagine that was 100% of the time. In fact, if I take that out and that out and just run that one again, if it's a clustered index seek and it's 100% of the cost, then that's fine. There's nothing else you can do to make that any better, because an index seek is the fastest type of operation. If, however, you saw this one and it was, it's got a table scan in it, then you already know that that's going to be a problem. But if that table scan was only 1% of everything that happens in here, like in this case, that table scan is 1%, guess where we need to spend the effort and the work? We need to spend it here, particularly because of the ordering of this join. If we swap that ordering round, you'd probably find that the customer's table would incur most of the work, because it's effectively trying to find the row it needs first before it then joins the other table. So table scans are bad, but work on the ones that have the highest cost. Like I say, if the highest cost is, most of it, 99, 100% of it is a clustered index seek, then you're probably not going to make the thing much better. So remember, measure, try, measure again. Look for optimizing your most heavily used pieces of code. If you're running things across whole data sets like analytics, statistics, trends, those kind of things over perhaps tens of thousands, hundreds or millions of rows, then, really seriously consider taking a backup of your live database and running your analytics against the copy of it. And the reason is you can then drop a load of the indexes that are no use to your analytics. You can potentially create other ones, but you just end up with a system that you can just concentrate on that. So hopefully that's been a fairly useful introduction to indexes. Hopefully you can now take that and kind of understand how to navigate your way around SQL Server using the query analyzer, using the client statistics if you want to do that. And hopefully this is going to give you what you need to start creating some real optimal indexes. So hope you enjoyed that. Any questions or comments, as always, please put them below the